Hello. Hello. Solutions and solubility guidelines. We're going to hit up the different types of solutions, so some definitions, review.
And then on to table F, how do we use that thing?
And we're also going to show you how to do double swap reactions, double replacements, and predict if the product is soluble or insoluble.
Yes, will precipitate form. So first off, but
definition. Solution implies that there are two substances that have mixed to form one new substance that is the same throughout. So when you put a solute into a solvent, those solute atoms, molecules, however you want to look at it, spread completely evenly throughout the entire solution if it's
he's
soluble.
really good at charades, by the way.
So-
really good at charades.
That is the definition of a solution.
If
being a
either of us
homogeneous
use the word
mixture.
solution from here on out, that implies that instantly, okay? Because that's what a solution is.
Now,
Solute is the substance in the solution that is being dissolved, by definition, smaller in quantity.
and that leads us to the solvent, which is the substance that does the dissolving and by definition is in greater amount. So my imaginary example, salt, solute, water, solvent, salt goes into the water, dissolves,
Salt water is a solution.
spreads perfectly evenly.
Maybe
throughout,
gargle it if you're getting
making
a
it
sore
a
throat.
homogeneous solution.
Yeah, no, don't be mad at me. There is a lot of room here, Milks. But listen, dissolving and dissociation, you need to know the difference. We're going to get into it a little bit more in depth. So dissolving is the first step when the actual molecules of the solid break apart from their neighbor molecules
Go into
and
the water,
full molecule. But, right?
water
all the way
hydration
around it.
all around.
Okay?
So-
That's dissolving.
The solid goes from the solid to the particle model where they're dissolved around all the water.
Right, and lots of things dissolve, but not everything dissociates.
Right.
Now, dissociates is when those actual molecules break apart into their ions.
And the ions can then move around separately and freely.
So ionics do this, covalence does not.
Now that leads us to this term that we use all the time, like dissolves. Like does need a little bit of description. It is our saying to help us remember that only polar solutes will dissolve in polar solvents, and only nonpolar solutes will dissolve in nonpolar solvents. If you have a mismatch, meaning polar one, nonpolar the other,
Right,
it's
so-
not gonna mix.
Right, so polar,
Like water's polar. If I
And
put a
polar,
polar
so
solute
this
into
is-
it will dissolve
so this is dissolved.
because they are like.
But if I take a polar and a
Non-polar, like oil and water, they will not dissolve. Okay, that's why oil and water salad dressing separates, because water polar, oil non-polar, they don't mix.
So I got a non-polar with a polar.
Not gonna mix.
Right. So insoluble.
Good word use.
Thank you. I wanted to choose a better word.
Non-polar like oil with another different type of oil,
soluble.
wax, soluble.
Now, I noticed
For
they changed
sure.
them up.
will dissolve, won't dissolve, soluble, insoluble.
Means the same thing.
Ooh, it does. It does. Here
So
we go.
let's
moving
carry
along.
on here. Alloys, these are really important to our human lives. It is technically a solid solution, a mixture of two or more metals, producing more desirable effects like
Of some
strength,
sort.
durability, reduced weight.
Yep.
All the tools in my shop at home are alloys. If I had made my tools out of pure iron, they'd be rusting just sitting there on the bench.
Yep.
Mix another metal in, doesn't rust.
They would rust with the water in the air.
Yeah. Now
We changed this. We got away from aqueous, was a little bit of a pigeonhole. We went straight to just liquid.
Mhm.
By definition, solutions will not settle upon standing. That's muy importante. Water is what we call the universal solvent because it's polar, but it's also a covalent. So that's kind of it can do polar and non-polar, it can dissolve all sorts of stuff, but it's not the only solvent out there. So there's some more polar solvents that do stuff. There's some more non-polar solvents to dissolve other things, and that's where we get the like it dissolves alike.
Because not everything's going to dissolve in water. Not every time you're going to try and dissolve something in water. So water does a great job. It's always our exception to these rules. That's why it's universal.
Right.
But
Colloids.
three types of non-solutions. A colloid is not a solution. It looks like one though.
It does look like
Fails the Tyndall test, which we'll tell you in a minute.
suspension is, I don't even like the word, but it's two visibly different things. So think of like coffee grounds in water, fall right to the bottom, dirt in water. I can separate them out. They will separate upon standing.
You shake them for a minute and it might look like a solution,
And it
but if
changes.
you come back an hour later, it's changed.
Right.
So
Emulsions is a fine dispersion of liquid droplets or minute droplets that aren't really soluble or miscible, but it really will kind of look like
Mhm.
a solution. And we got a good one for example for that.
Milk.
You might have one in your fridge. Yeah.
milk or mayonnaise.
Right.
These are technically not solutions or emulsions because if you look at them under a microscope,
They're not the same throughout.
they're not the same.
The Tyndall effect is we use a
Laser.
laser beam.
You get a laser beam. You can see the dot on my hand maybe. If there was a solution in between us, the laser and my hand, the solution, you would not see the laser beam traveling through the solution. But if it was a colloid, a suspension, or an emulsion, you would see the shaft of the laser beam throughout the body of that solution.
Right. That implies that the particulates in the, is it a solution or is it not, are so big that it will reflect the laser light towards your eye, showing you that it's not really a solution.
Table F.
How do we read this, Mr. Monaco?
Draw me a funnel.
Funnel. Like that,
Mr.
you mean?
Milks? Yeah. What gets stuck in a funnel if I'm doing a filtration?
The stuff that's not soluble.
Good. That's exactly how I look at this chart. If you're in the middle of the chart, you're an insoluble compound, means you will not dissolve. If you're on the outside, either sides of the funnel, you are a soluble compound, which you will dissolve. So, how do we use this dang chart? Well, you got to learn about using the chart by looking at the names and the formulas of chemical compounds. This particular one, as we know, is sodium chloride. Now, the best way to use the chart is to use the anion, the negative ion first. Go find it on the chart, Cl. So Cl there is the soluble compound. And then you look to see the cation, the positive part, the Na, the sodium. It's not an exception to the rule. So therefore, this compound is soluble. Okay? So that is how we write an S for sure. Now, next chemical, AgCl2, so silver chloride. Again, we're going to use the chloride part to find our place in table F. There's chlorine again. It says it's soluble, but wait, got to check the exceptions. You look to the cation, the metal ion, the positive ion, the first half of the formula, and you see if it's in the exceptions rules. If it is, then you got to go away from what that title chart heading said.
Yeah,
So if
exceptions is the opposite.
right. So if it was soluble, an exception to it is insoluble. Now, AlPO4. Just because it's a polyatomic ion doesn't mean you should panic. Aluminum phosphate. Okay, so we're going to use that PO4, and we're going to find PO4 on the chart somewhere. There it is. Now, the chart does include the ionic charge of the polyatomic ion, and it says phosphates are insoluble unless the metal ion or the cation is from group number 1 or ammonium. And aluminum is not from group number 1, it's from group 13, so we'd have to call this insoluble. Now, the last little bit of this lesson is to do a double replacement reactions and predict the solubility of the products. So when we're determining the products of a reaction, it's really, really easy. You take the first metal and put it with the second nonmetal, and you write the new formula, MgCO3. So you see how we're doing brackets, first to last, last to first. So MgCO3 and NaBr. And then all you would do is you'd go to that chart F and decide which one's soluble and which one's insoluble. I do believe that magnesium carbonate, find carbonates here, carbonates are insoluble unless group 1 or NH4. Magnesium's group 2, so I know that magnesium carbonate is insoluble. And bromine, bromides, Br, halides are always soluble, especially when sodium's involved. So we call that soluble. And in this case, that S is not solid, it means soluble.
Yes.
And I means insoluble.
Yes.
Now the next one, again, we're going to go first to last, and then last to first. So the new compounds we're going to make are ammonium
So I remember
chloride.
I remember in class when I've seen you do this. You would do
Yeah,
that.
I was at top and bottom.
There you go.
So we're going to make ammonium chloride, so NH4Cl.
Notice I'm not bringing over the 2 on the Cl, and I didn't bring over the 2 on the Na and the
These
Br.
are not balanced necessarily. We're not balancing here. You can balance them, but we're just trying to show the
But you
products.
still got to
and
do the
solubility.
crisscross if you're going to balance. You can't just bring over the subscripts. You got to do it and then crisscross the charges, build them, and then balance.
Okay, so now we look and see chlorines, halides, group 1, they're always soluble, so that's soluble. Carbonates, CO3, are insoluble unless ammonium or group 1. Calcium's from group 2, so that is insoluble. That's our solid precipitate.
So you're going to find, we're going to ask you to circle those.
Yeah.
That's it.
Thanks. See ya. Buttons.
Everything worked out perfect.